Hello. Okay, this is you don't need any of this preamble presentation to learn Python. Uh, but the way Python or most scripting languages are usually taught uh, kind of just throws you right into the code with no sort of context at all about like, what is physically happening on a computer. And I have found that that can often create confusion and sort of standing up and understand like just a basic understanding of what's going on before you jump right in to coding can really help kind of build a mental model of what's going on. So and the mental model does not have to be super high fidelity and accurate. It just has to get the sort of like basic concepts, so you can kind of organize your thoughts and sort of understand behaviors you might be seeing from the program. Uh, So this preamble is all about that. It's about sort of the level of, and you know, a lot of people who write code don't even have this sophisticated of a mental model of a computer in their head when they're doing it, and you don't necessarily need it, but it can definitely help. Hopefully, you find it interesting. Um, I find that code is easiest to write when I'm sort of understanding where the data is, uh, and how I'm gonna use it. Um, so software in general, you know, we build it on these layers of cascading abstraction. You know, it's kind of like an onion. At the outer side of the onion, you really don't know what what's in the core, but you need what's in the core because you know it's holding everything up. You know, example of this might be networking. Like, you know, from our level in Python, we're going to just be kind of getting data from the internet, and we don't really have to think about the details of like, oh, how, what is transport control protocol, and how does it make it so the internet doesn't just grind to a halt with a traffic jam and all that stuff. That's kind of like buried in a lower layer, but if we know that it exists and basically what it's doing, it can help us reason about like, oh, why isn't my program not working the way I thought it should? So WTF is a computer. Very, very simply put, it is just a machine that is designed to move data around between different devices and do very basic arithmetic on that data. Um, this diagram kind of represents the fidelity of a mental model I have in my head when I'm writing systems level software. Uh, you know, the main component here, well, there's two main components. There is our main memory, you know, random access memory, RAM, and there's the CPU. Kind of like, you know, in baseball, where, you know, there are nine players on the field, but most of the time it's really only all the action is between the pitcher and the catcher, and everybody else is just kind of standing around until they're brought into play. The CPU and the main memory are kind of the pitcher and catcher in this baseball analogy. Most of the activity is going on between them most of the time. Occasionally, these other devices come into play, usually when you're moving data around. So on the left, we have our disk storage, right? So like lots of data. You know, it used to be disk. Now it's mostly solid state stuff. So there's actually not anything spinning anymore. But you know, we might have terabytes and terabytes. You know, if it's if it's a big data farm, you know, they could have petabytes of storage. Um, we have our input devices and our output devices. Some devices are both, like, you know, a keyboard's an input device, a monitor's an output device, a network adapter is an input and output device. But the thing that all of these have in common is to work with any of the data you're getting from them we're sending to them, that data has to flow through main memory or RAM. And for example, on my laptop, I have 16 gigabytes of RAM. Back in the day, that would have been enormous and cost many bajillion dollars. Uh, and most architectures now are 64 bits, meaning that each one of these slots, it has 64 bits of information. That would be 8 bytes, and so if you do the math, that means there are about 2.1 billion addressable memory slots. So each one of these 8-byte words is addressable, like it has a numeric address, and we can refer to it and get the contents that are there. So like when you load a file off of disk, it's going to read whatever the size of the chunk you told it to read off disk into memory, and that's just going to stack up here. And this transfer, right, is slow from disk to main memory comparatively. We don't need to know how fast it is. Oops. We just need to know that it is slow. The next stage in the process here, like when you want to actually operate on the data in memory, and that's when our CPU comes into play. And most CPUs nowadays have more than one core. And all CPUs have a clock. And clock is usually, it's a quartz oscillator. It's spitting out about 20 megahertz. And then, there's some electrical engineering magic that kind of locks that in this like phase lock loop that actually generates, on the order of like a 4 gigahertz signal, which means that every quarter nanosecond in a lot of modern CPUs, there's an electrical pulse that comes through and steps this CPU. And what happens on that step is, each of these cores will have several registers, and a register is just like a memory slot in main memory. It's going to be a 64-bit word. And one of these registers is going to be an instruction register. That instruction is going to be a basic operation. Most CPUs architectures these days have on the order of like 50 total basic operations, and there are things like load a memory address into a data register, or add data register 1 to data register 2, or move data register 3 to data register 4. Like, these are the basic sort of building block operations of a CPU, and each time this clock sends out an electrical pulse, the current command, the current instruction is executed on that CPU. Like, it runs through all the itty bitty little transistors and does all its fancy schmancy electrical engineering shit we don't need to know about. And it will execute the operation. So, you'll notice here that there is also this cache memory. This isn't super important. You never have to think about this really. This is hidden from you by the hardware. But just to give you a little bit deeper window into what's going on here, right? Like, when a program that is executing commands says, I want a memory address, frequently what's going to happen is your CPU is not going to just load that one memory address. It's going to load like a block of memory addresses into cache. And then it is going to load the one that you asked for into the register you asked for from cache. Now, the reason it's going to do that is for speed. So going from main memory to cache is faster than going from disk to main memory, but going from cache to core registers is much, much, much faster than going from main memory to cache. So this is just like a gamble that the CPU is making. It's saying, I bet if this program is interested in this address, probably next time I do an instruction, it's going to be interested in this address. And so it's just this cost speed saving mechanism. And there's like a lot of that implemented in the guts of computers that we don't really have to think about it, but like know that it's there. And sometimes programmers do have to worry about this stuff where if you're doing a huge amount of data processing and it's really running slowly, you might kind of like take your basic mental model of a computer and go apply it to look at your program and see, oh, like I'm accessing a lot of like random bits of information from all over the place in this file, and that's probably resulting in a lot of cache misses. A cache miss being defined as the core says load address blah, and it goes and looks in the cache for address blah and sees that it's not there and says, oh shit, I have to go back out to main memory and load in a new block. So like that's a basic example of how you might apply your mental model to your program, but most likely you'll never, especially if you're just doing like sort of basic data analysis, most people never even have to think about it on this level. But knowing that it's there can kind of demystify these sorts of things. So like for getting information from input devices, in your Python program, sometime you might use the input function, and that function, it gets input from a keyboard, so it just sits and waits for me to press a key, and when I press that key, it's going to return that character. And under the covers, what's going on here is when I press that key, there's some hardware that sends an interrupt that is intercepted by our operating system, which we'll talk about next. And the operating system is going to take that data over some bus, and a device driver has been written that knows how to do this, and it's going to put it in memory. And then our operating system is going to give that memory address to our Python program under the covers, and then voila, we have a character. Similarly, outflow of data, like when we, the windowing system keynote that I am presenting on right now, it has computed this image from the SVG file that it is, and has decided what all the different pixel values are. So there's this two-dimensional array that has basically blacks and whites, and it's sending that to memory, and it's existing in our memory in a contiguous chunk. And then at whatever the refresh rate is, 60 hertz or whatever, it's being written out to our screen, which knows how to take that two-dimensional array and actually turn it into uh, I'm assuming these are diodes uh, into the different light colors. There's one more thing I include on here, just kind of highlight that there are different kinds of CPUs. So, oops. Down here we have a graphics processing unit. And GPUs are CPUs. The only difference is instead of having an instruction register for each of the cores, it has one instruction register for all of the cores. But the cores can have different data registers. So what that means is it does the same operation each time this GPU is pulsed. It does the same operation on different data for each core. And that turns out to be, I mean, the reason we have this is for 3D processing. That was the initial need. Like game designers and people who are doing 3D rendering, it was just too slow to do this on this architecture. When when you when you look at the math involved in 3D rendering, it's a lot of vector operations. And it just so happens that doing that in a single instruction, multiple data way is much, much faster. Nowadays, these are used to like train neural networks and all that kind of stuff. A lot of scientists have figured out that the mathematics of their particular computations map much better onto this architecture than CPU architecture. So these are used for science, gaming, and artificial intelligence these days. But the way this is working is like let's say it's a video game's running on a core and it's executing instructions, and it is building a scene, like it has in memory sort of representations of all of the objects that are in the scene and sort of definitions of their surfaces and whatnot, and it packages all that up into memory, sends it down to the GPU. The GPU runs its computation. GPU sends back the pixel mapping for the screen, and then that gets output to your device. Um, so uh, this is, whenever I'm writing a program, this is about the level I'm thinking about what's happening on the computer. I mean, obviously, you can dig a lot more into each one of these components. There are whole semesters of graduate education you can take on each one of these, but like, unless you're dealing specifically in one of these areas, you really don't need to like have a more sophisticated mental model of a computer in your head than this. I just wanted to add a little addendum to this slide. Um, so it used to be that people actually programmed processors directly. Like you would sit down on a computer and you would type load, memory address blah into register blah, add memory address blah into register blah. I have done this. It was a course I took in college. It was a lot of fun. It's called assembly language, and you're working directly with the opcodes. We worked in x86 architecture, which is an old Intel architecture, from the 70s that we're still sort of living with the descendants of today. Um, but I just wanted to give you an example of something in the real world that has been programmed directly uh, in opcode or assembly language, and that is the control system for the now retired space shuttle. It was about 400,000 lines of assembler, and it's probably one of the least buggy pieces of code ever written because it was tested out the wazoo. And I just think that's really fun that engineers in the 70s sat down and wrote out 400,000 lines of assembler code to control the space shuttle. So the thing you'll notice about this is that there are a lot of resources. We've got all these devices connected up here, disks, input devices, output devices, GPUs, network, not really shown here, but it's a big one. And we've got a few cores, not many. I think my laptop has 8 on my CPU, so it can be doing 8 different things at once. But we only have, one sort of contiguous chunk of memory. There's, you know, a pipe between it and cache. And, modern architectures might have like several banks of main memory all separated, but, we can just assume that there is just one. So, there needs to be something that organizes and controls access to all of these different resources, because if we've got different things running on each core and they all want to use the keyboard at the same time or the disk or the network at the same time, you're going to have issues. So that is where our operating system comes into play. Um, and I asked Dolly to make me an image of a conductor of a symphony, because I think that is probably the best analogy I can think of for what an operating system does. The operating system here is the conductor. And when the computer is moving along and all these different programs you have open at the same time are successfully doing what you're asking them to do, you're making music. And the thing that keeps all that music in tune is the OS. So think about all of the players in this symphony as the different processes that are running, the different programs that are running on your computer. They're all asking for different things at the same time. Um, one of the core things the operating system does is schedule processes time to run on the CPU. So like usually we have many more processes alive and running on a system than we have cores. They can't all be running at the same time. So what an operating system has to do, every operating system will have a component in it called a scheduler, and that scheduler time slices time on the CPU for each process. Kind of, and there's like, many PhD theses have been written about how to write an optimal scheduler that performs well, and because you might have some processes that are much more greedy, they have a lot of instructions to execute. Other processes might be sleepy. They actually don't have much to do right now. They're just kind of sitting there waiting for input. And your scheduler needs to be smart and kind of know about those things and schedule time considerably. Like and when it schedules time on a CPU, it sets a hardware timer that will interrupt execution and give the operating system a chance to switch all of the registers out on that CPU, uh, or on that core in that CPU, and then switch a different process in. Load all of its state when it was last switched out needs to be maintained, like all the values of all the registers, and they need to be reloaded back in so it can start executing it where it left off. And this is happening many times a second uh, on your laptop right now. And that switch from one process to another is referred to as a context switch. There is some cost to it, so you don't want to just do it all the time. Kind of think of a traffic cop. They don't let one car go and then another car go. They kind of let rows of cars go. But the operating system controls access to all of the system resources. So like, processes, when we write a program, like we do not have unfettered access to the machine. The operating system mediates our access to it, and it provides us sort of a nice interface to, say, get data from a disk, or get a file from a disk, or get input from a keyboard, or we different processes have different amounts of memory they want to use. Um, so the one bit of terminology I think you need to leave here with is the system call. And operating systems, for example, the Linux kernel provides a bunch of functions called system calls that allow access to these resources. So like when you want data from the internet, in Python, there will be some high level functions that we call, but under the covers, Python is actually going to make a system call to Linux or to OS X, whatever machine you're on. It's going to make a system call to that machine's kernel that knows how to talk to the network interface card, and knows the TCP/IP protocol and like how to get data. And then we don't need to know how any of that works. We just need to know that, oh, we called the operating system and it returned a bunch of data. Now we have it in memory and we can do math on it or whatever we're going to do. So, operating systems organize the chaos. Okay, so on this next diagram, there's a lot going on here, but we're going to take it step by step. And the goal here is kind of map maybe what's going on in some code to kind of what's going on uh, in memory on your CPU and with the operating system. So we've taken our first computer diagram and we've just kind of broken out the main memory and the CPU here. And we're going to define a few terms. The first one is processes. Now, a program might be like Keynote, like I'm presenting on right now, or, Adobe Illustrator or Chrome. Like those are all programs. Each one of those programs might actually be composed of a bunch of different processes, depending on how the software engineers decided to architect those programs, or they might just be one process. a process is, well, let me back up for a second. So in main memory, when our computer boots up, the first thing that we have in main memory is our operating system kernel. The kernel is the core of the operating system that knows how to manage the hardware. It has the scheduler in it. The kernel has defined a bunch of concepts for us in software. Uh, and one of those is the concept of a process. So when you launch a program, what is happening is a system call is being called in the kernel. Like there is code in memory here, um, and there's a function called uh, fork and another function called exec. And when you launch a process, your interface, whether that's the terminal or the graphical interface on Mac, under the covers, eventually those two system calls are invoked with the path on disk to the executable for that process. And so the operating system will take that executable and load it into memory. So let's say process one has just been loaded into memory. It's sitting here. And what is in memory are the instructions. So like the moves, the adds, the instructions are called opcodes. And so the actual code that will be run on the CPU is just sitting there in memory. And then the operating system will decide, okay, I'm going to schedule you a time slice to run. And so it'll load your first instruction onto the instruction register of a core. And the next time the CPU pulses, that instruction gets executed. And maybe at that point your process starts asking for memory. Like you have allocated a list of integers or something. The operating system is where you go to get that memory. So your process will make more system calls to say, hey, I need an array of length 10. So I need 10 memory addresses to store my array in. Then your operating system will conspire with your CPU. Most CPUs have this component called a memory management unit. And under the covers, your process isn't actually using the physical addresses of memory. We've kind of abstracted that into virtual memory. So you're given and the only difference between a real hardware memory address, like let's say memory address 0, and virtual memory is that virtual memory is just a mapping. So we have like this space of addresses that aren't real, but the MMU has the mapping of our virtual addresses to the real addresses. And so say process 2 is loaded at memory address, I don't know, 1 billion. Our virtual memory first address might be 0. And so when our process then says, oh, give me an array of length 10, it's going to say, okay, memory addresses 0 through 10 are going to be that array. But in reality, it's like, 1 billion through 1 billion and 10. Now, this, you never have to think about this unless you're programming really close to the metal. But this is kind of I included this just to kind of show how the operating system mediates access to the hardware, because a thing that your operating system is also sort of a security barrier. So a thing that might happen is process 2 here might say, oh, hey, I want memory address, X that might actually map to somewhere in user processes 1's memory. And that is not allowable. If that were allowable, you could, get passwords out of memory and stuff like that. So the kernel will say in the MMU conspire to say, oh, no, you can't do that. And when that happens, that's called the segmentation fault. You may have encountered one in a program that failed. It usually just means that a programmer made a mistake and ended up trying to access some memory from a garbage address that wasn't actually real, and that'll crash the whole program because the kernel will be like, "Yep, you can't do that. You're in timeout," and give you the boot. And it's not just like you're not allowed to do that. It's also like, it doesn't it might not, it might be meaningless what you asked it to do. So there's really no choice but to crash out. Okay. The other thing that's going on here, so we have processes, but we also have threads. Threads are another concept that are defined by our operating system. They actually, weren't, they haven't been around since the beginning. Processes used to be, all there sort of was. So if your program had to do more than one thing simultaneously, you were talking about launching several different processes. But the operating system has, I mean, there's a lot of overhead to a full context switch, like fully unloading one, say process two off of core one, and then loading process one on core one. Um, there's a lot of overhead in that context switch. Um, and the other problem is that process one and two were part of the same program. They actually can't see each other's memory because of our security stuff in this virtual memory thing. They aren't allowed to see each other's memory. So if they want to communicate, they have to use a pre-approved like inter-process communication protocol, you know, offered by the kernel. Like the kernel will say, okay, you can make some system calls to the kernel to reserve some memory that you both can have access to, and that's how you would communicate. And that sort of coordination is sort of hard to navigate for a programmer sometimes. So to solve these two problems, one, the performance problem, and two, let's say you need to do two things at once, uh, the kernel has offered this new concept called a thread. And a thread differs from a process in uh, those two subtle ways. So first, there's a little bit less bookkeeping that the kernel has to do to keep track of a thread, so that when it loads a thread off of a core and puts another thread from the same process onto that core, the context switch, there's a little bit less it has to do, so the context switch is faster. So it's faster to load. One process can have many threads, and a thread, I mean, it's short for a thread of execution. So um, in our diagram here, process two only has one thread, so it's only executing one set of instructions at a time. Process three has two different threads running, one on core two and one on core three. And so a thread is just a sequence of instructions. So in memory here, we have different sequences of instructions. There are calls that we can make in those instructions that will create threads. There are system calls that will call onto the kernel. The kernel will create a thread, and that thread will be given like an initial start instruction. And so process three here has created two threads, probably, but maybe they're both pointing to the same instruction, or maybe they're pointing to different instructions, but let's just say they're doing different things. And so this gives the operating system the ability to schedule more than one execution path for a process on the same memory at the same time. So the other key difference is these two different threads on process three here, they both can see the same memory. There is no memory access control between them. So the instructions running on thread two can go access, memory address 5, and so can core 3. Now, there's a problem that comes up with that, and that if these aren't synchronized and they both try to access the same memory at the same time, depending on the logic of your program, that might break your program. So it is up to the programmer if you need more than one thread to synchronize them. And the operating system, again, provides us a mechanism to do that. And this particular mechanism is called a mutex, which is short for mutually exclusive lock. So you can just say, oh, these series of instructions, only one thread can execute them at once. And that's kind of how uh, we keep them synchronized. You probably won't need to ever, like if you're just doing data processing with Python, you might not need to use threads. Like if you're processing, if you need to speed up your processing, and it's amenable to breaking it up into different tasks and doing those simultaneously, you might want to use threads. But just knowing they're there is helpful because you will encounter the terminology around the internet. Um, but you know, definitely initially, I wouldn't really worry about them. Just know that they're a thing. They're a way for one process to have multiple different threads of execution simultaneously, uh, working on the same set of memory. Okay, so we talked about processes and threads. Um, Next thing I want to do is kind of look at a simple program and kind of map some of the things in that program back to what's going on in hardware. And to do that, we're going to look at this myprogram.c. So this is a C program, and I know we're trying to learn Python, but stepping down to C, which is a compiled language, like the kernel is written in C, uh, we see more how it's using the hardware directly. Um, so as I said, C is a compiled language. So when we run myprogram.c through a compiler like either GCC or on OS X, Clang, Microsoft Visual Studio, and the compiler reads in the file, it reads in this text, and it translates that into machine opcodes. And the files that it spits out are executables for specific processor architectures. So, in laptops now we have Intel processors. We have, the MacBooks just transitioned from an Intel-based architecture to an ARM 64 architecture. Um, and this is why some programs used to work on Mac and no longer do, just because the instruction set, the set of opcodes on the CPU, has changed from x86 to ARM, and so now everything needs to be recompiled and rebuilt to run on ARM, and that might involve a little bit of engineering, which is why some programs are lagging. So a few things to know about C. C, in addition to being a compiled language, like most compiled languages, it is what's called strongly typed, meaning anytime you allocate any memory in a C program, the compiler has to know how big that memory allocation is. And that's what we really refer to as a type. So in C, we have a number of different types for numbers. There's integers, there's integers of various sizes. By default, I think this is going to be a 64-bit integer or a 32-bit integer. I forget where the standard is right now. Character, char for short, is going to be a 1-byte character. There are float types. There's Boolean types, 1 bit. The float types, they think decimal numbers. There's a floating point standard that you can go look at. But the thing to know is that each of these types are, the space that they take up in memory is defined, and the compiler knows that if you're working with an integer, it's going to be 32 bits. The other thing that's going on here is we got three functions. Like pretty much every programming language has the concept of a function or a subroutine, meaning just a block of code that you can call to do a repetitive task. Like, there's a lot of repetition in programs, and you don't want to have to, write that code each time you need it. So you just stuff it in a function and call that function when you need it. And so in this program, we've got three functions. Main down here. In C, the standard start point of a program is called main. And so when you tell your operating system to start executing this program, the first instruction that's going to be loaded into the instruction register is going to be at the start of this main function. Um, so and functions take arguments, like up here make string. This function, this function takes an argument of type integer, and that we've named it size. So there's a variable called size, and it is an integer, and we're passing it into make string, and make string can then use it in its block of code. End functions have a return value. If they return nothing in C, it's called void. But here we have a few different return values. Again, the standard signature for the main execution function of a C program is main, and it always returns int. And by default, a return value of 0 means that this process has exited successfully. There were no errors. If you return a number greater than 0, the operating system by convention just interprets that to mean something went wrong. Now, this program is doing something really sort of contrived. It doesn't really make sense what it's doing. Like, so don't think about, oh, well, why would you write a program this way? This is just contrived to show us some examples of, program flow and what a stack is. So if you look over here in main memory, and we look at our process memory here, you'll see that there's one section of it that's just going to be the program instructions, like the opcodes. Like when we compile this C program, each one of these lines is going to kind of turn into a bunch of different, individual machine instructions. That's what the compilation step does. Those machine instructions are in the file that the compiler spits out when you load that file into memory. They're just sitting there in memory, ready to get loaded into the instruction register and executed on the cores. Then we have data. So these are going to be all the variables that we define in our program. And in a C program, and in many programs, there are two main types of memory reserved to hold variables. There is stack memory and there's heap memory. And these refer to sort of how the data structure works for these memories. So a stack is, just think of a stack of papers. You can put a piece of paper on top of your stack, and then that last piece of paper you put on top of the stack is the piece of paper you see. And so you could also pull, or what we call pop, that piece of paper off of the stack, and then you see the piece of paper under it. So you can add things to the top of the stack, build it up, build it up, build it up, then pop things off the stack, and tear it down, tear it down, tear it down. And then a heap is just what it sounds like. It's just an unorganized heap. And the process might have pointers to addresses in this heap kind of randomly, and can access them over time. And the use for these two different kinds of memory storage come from our program structure and flow. So a stack is, you can think of it, it's a last in first out queue, like LIFO queue, as we just said. And a term you will hear, even in the development of Python, is the term call stack. And that's going to that's going to refer to sort of the function history at your current point of execution. So in our program here, we have this main function. It calls, one of the first things it does is it calls bar function. And bar, the return value of bar is a character, and we store it in this variable bar string. So let's just follow this execution down. Main calls bar. So here we enter into the bar execution. The first thing bar does is call make string. And so now we enter in make string. If we were to stop right here and look at our call stack, this is what it looks like. So first we were in main, then we entered bar, and then we entered make string. Now, anytime in one of these function definitions, if we create a variable, oops, like right here in make string, we are creating a character variable string. If we create this variable, this variable needs to exist in memory, right? We're going to be operating on it. So this is going to go on the stack because it is scoped. It's what's called scoped to this function. Like bar cannot access this particular variable unless we return it to bar. And but we might declare other variables in here that we aren't returning, in which case the bar function can't actually access that memory. So that also means we're not going to need that memory after make string returns and is no longer executing. So this naturally is sort of a stack data structure. Like when bar calls make string, a new frame is allocated on the stack, and that frame is going to be, a certain size, and in that frame are going to be some bookkeeping things about the return addresses, of where the return value should be stored, but it's also going to contain all of the variables that are allocated in this function. So, and then when we return from make string, this frame at the top of the stack is going to get popped off. And along with that pop, all of the local variables that we declared in make string are going to get garbage collected. They're no longer considered to be in use in memory, and so that memory can then be reallocated later. Like we can be confident that no other point of the program is going to need to access them, so we get rid of them. Now, when your program loads, the kernel will reserve um, a reasonable amount of space for your stack to exist, and your stack memory is contiguous. So it's all lining up next to each other, and you can add to it, add to it, add to it, add to it, and it gets bigger and bigger and bigger. And if it gets too big, and you run out of stack memory, that is called a stack overflow, and that is where the website Stack Overflow gets its name, and that is an error, and your program will crash. Usually that only happens if you've made a mistake, like, functions can call themselves. That's called recursion, and sometimes the design of the program warrants it. But when you have a recursive function that's calling itself, at some point one of those calls will need to make a decision to not call itself, or else you're just going to be an infinite loop of a function invoking itself over and over and over. So most of the Stack Overflows people run into, and it's possible to do them in Python, are because of an error like that. Okay, so the heap is sometimes you need to allocate some memory that is available anywhere in the program, and that's what the heap is for. And so we do have one example of that allocation here. So there's this function call that we've included from one of the C standard library mechanisms, which makes a system call to the kernel called memory allocate, or malloc for short. And this just says, give us size many bytes on the heap. So what this program does is it calls bar calls make string with passing 3 as the argument. Make string creates 3 bytes of memory on the heap, and then the return value of malloc is a pointer, not the actual value of this string, but a pointer, and that's what this little star denotes here. A pointer to the first character that was allocated. So existing in this variable, which is actually allocated on our stack, is the memory address returned by this call to malloc, which is on the heap. So we have a stack variable on our stack that is pointing to a memory address on our heap. This function then returns that memory address. We have it on the bar stack frame. We have a string variable that is that same pointer value because it was returned to us, and now we're just storing it in our stack frame. And then we have this line of code here which assigns these 3 characters to the string. We dereference what's called dereference the pointer address. So this is just telling the compiler, okay, when you compile this code, what I'm trying to do here is at the string memory address, I want you to store these 3 characters. And we know we can because we allocated 3 bytes of data. So we can definitely put 3 bytes starting at that memory address. So then bar returns that pointer again. So bar is returning a pointer on the heap, but now the 3 bytes starting at that pointer address on the heap contain the characters BAR. And so now we're in main. And we're just going to print that string out to memory. And then you see this call to free. The thing about compiled languages in C is you're doing all this memory management yourself. Anything you malloc or allocate on the heap is going to live on the heap until you explicitly free it. And if you don't free the memory after you're done with it, and you keep allocating more and more memory, that's called a memory leak, and your program can use up all its memory and crash the system, or your operating system will police that in some way. The good news is in Python, we don't have to think about any of this really. Knowing that it is being taken care of for us can help you kind of build a better mental model of what's going on in Python, because it's just kind of doing all of this for us under the covers in terms of managing the memory addresses, freeing and allocating new memory on the heap. In Python, it's pretty easy to code a lot of Python and not even really think about what's going on the stack and what's going on the heap. Internally, the way Python is implemented, it's even a little bit, the lines get blurred between these two things, and you might see that when we get into how Python scoping works and how that might be a little bit different than this. But the takeaway here is memory exists, and when you are declaring variables and working with variables, they are stored in memory in some way. And one of the hard things about programming is keeping track of that. And Python does a lot of that hard work for us, but we should understand and know that that's what's happening. Okay, this is the last, as the gray hairs, the gray beards say, view graph of the preamble. Python is a bit different than the C program we just looked at. The C program we just looked at is compiled. Python, the language Python, when we program in Python, it is what is called an interpreted language. And that means it's running, there is a compilation step, but it happens when you run your Python script. So Python itself, so let's look up here. So Python itself is written in C code, like the code that we just looked at. Um, there is a standard implementation. So Python, the language Python is a specification, so anybody can implement to that specification, but the standard implementation is something called C Python. And C Python is compiled, it is written in C, so it is compiled into an executable called Python. When you launch a Python program, so here we have written the last program we looked at, this is sort of what it would look like in Python. So when we invoke our Python script, the way we do it is we call Python, we tell the operating system to execute the Python executable, and we pass the path to our script in on the command line. And then after that, we have any arguments that we want to give to our script. Internally, what Python then does is, so the operating system has launched Python. It is in main memory. This is the Python interpreter. And the interpreter has two main components. The first one is the Python compiler. And so this is the code that goes and loads your file from disk, reads it, and compiles it to Python bytecode. So you might see on disk that when you're running a Python program, Python will create some directories called underscore underscore pycache, and in those directories you'll see the names of your Python files just with the C addition to them. These are Python bytecode files that the Python interpreter has compiled your code to. And these instructions are kind of like the opcodes that would run on a CPU, except they don't run natively on a CPU. They run in the second main component of the Python interpreter, which is the Python virtual machine. So the way to think about this is that in our Python C code, the programmers have basically simulated what is going on in a processor, and we call this a virtual machine, and it knows how to execute these basic instructions. So this bytecode is actually what you see when you take this program and compile it. So what does this buy us? Like why go through all this extra rigmarole just to have a language? Why not just compile Python directly to a CPU? Well, it gives us several advantages. One is platform independence. So we can compile C Python to, Mac or Windows or Linux, but that code is all going to understand the same bytecode, so we can run our script on any of those platforms. We don't have to worry about building it or compiling it specifically for those platforms. Like, we can just email it to somebody and anybody can run it anywhere. The other advantage is simpler syntax, since Python here is a process. Like it's we don't have to worry about memory in the way that a compiled language would have to worry about memory. Our virtual machine can be complex enough. Like, hardware is very simple and the kernel is very simple, but our virtual machine can be as complex as we want it to be, since we're writing it in software, and it can do all of this memory management stuff for us. So you can see this is a much shorter program than the last one. We don't have to worry about, like, oh, this string that I'm returning, is it a pointer to a string, or is it a string? What's going on? The third advantage is something called introspection. This program, this myprogram.py, exists entirely in memory when we run it. Like, the source code and everything, and the bytecode, it's all in memory. So while it's running, it can actually look at itself. And it might not be clear why that's advantageous, but it can allow programs to kind of like do a little bit more dynamic things at runtime than compiled languages do. Because when you compile a language like from C and then you run Python, in memory, this source code is lost. It is no longer here. It might not even exist on the machine anymore. What does exist is just the compiled opcodes that are going to run on our machine architecture. So we've lost the ability to refer back to the code within the program. But when you can refer back to the code in the program, like you can do some more interactive things, and also the program can kind of rewrite itself while it's going. um, it allows you to do some fancier stuff more quickly that way. The disadvantages to all this, the number one disadvantage is it is slower. It is a lot slower than a native C program to do the same thing because you first have to simulate it on your virtual machine, essentially. And the second major disadvantage is in a compiled language that is that is closer to memory, and anytime you allocate memory for a compiled language, you allocate memory for a specific type. So the compiler kind of keeps track of, oh, this memory is pointing to strings and this memory is pointing to integers. Just going through that compilation step, it means that most of your sort of memory allocation errors and how you're working with variables are caught here in this step, like while you're building your program, versus in Python where the typing is dynamic, it happens at runtime. Um, those types of errors tend to be found when you run the program. So this can create problems if there's some execution path that is pretty rare that the program actually enters into, and then you send it to a user and they run it, and you've never actually seen that execution path, but then it goes in and it errors out at runtime. Whereas in a compiled language, it's highly likely that that specific error would have been caught when you did the compilation step before you sent it to them. So those are the two main disadvantages, but the advantages are so good for lots of different kinds of programming that most new code in the world written today is probably written in Python, and um, and because the language is so simple, um, it has attracted a lot of people to it, and because it is so popular, a lot of people have written libraries for it to do lots of different things, and this sort of builds and snowballs on itself. And the main reason people use Python now is just because a library exists to do basically anything that you would want to do in Python for free. Okay, so that's my brain dump, my mental model of computers, what they are, how they work, what the operating system's doing for us, kind of what Python is. I mean, we talked about memory, processes, threads, what a stack data structure is, concept of pushing something onto it and popping something off of it, system calls, compiled languages, interpreted languages. That's a lot. Like that's several years of computer science undergrad. So like, don't feel like you need to hold any of this in your mind. It actually might be like edifying to go back and watch this again after you've worked with Python quite a bit or gone through all the modules. Um, or maybe this was just at a level that like was you already knew and understood most of it, and I'm just mansplaining. But I think it's kind of helpful just to kind of get a bottom up understanding of some context of what's going on. So I hope you got something out of it. Let me know if you have any questions.